We're going to talk about systems with three variables, so an x, a y, and a z. The graph of an equation in three variables, such as ax plus by plus cz equals d, where a, b, and c are not all zero, is a plane. So a plane is somewhat of a three-dimensional line. You have an x-axis and a y-axis, and then you add that third dimension to it. You've been to 3D movies where the images pop out at you. You add that third dimension to it, and that creates a three-dimensional line, which in other words would be a plane. To graph an equation with three variables using the intercepts, you need to find the x, the y, and the z intercepts. Remember, at the intercept, the other variable, or variables in this case, are zero. Connect the three intercepts with a triangle, and then you extend that triangle out forever. When a line intercepts an axis, the value of the other variables are all zero. So we're going to graph the equation x plus y plus z equals 3. To graph that, find the intercepts. To find the x-intercept, you're going to substitute 0 in for y and z, because at the x-intercept, the value of y and z is 0. So if you substitute 0 in for y and z, you end up with x equals 3. So the x-intercept is 3. On a three-dimensional plane, it actually has coordinates of 3, 0, and 0. Y-intercept, x plus y plus z equals 3. We're going to substitute, to find the y-intercept, going to substitute 0 in for x and 0 in for z. Because at the y-intercept, the value of x and the value of z are both 0. So if you substitute 0 in for x and 0 in for z, you end up with y equals 3. So the y-intercept is 3. The coordinates of that point would be 0, 3, and 0. And for the z-intercept, at the z-intercept, the value of x and the value of y are both 0. So substitute 0 in for y, 0 in for z. End up with z equals 3. So the z-intercept is 3. The coordinates of that point would be 0, 0, 3. So at the x-intercept, the value of y and the value of z are both 0. The x-intercept is 3 in this case. At the y-intercept, the value of x and the value of z are both 0. The y-intercept is 3. And at the z-intercept, the value of x and the value of y are both 0. And in this case, the z-intercept is 3. So you have those 3 points, which you can make a triangle with those 3 points. So to graph this equation, make that triangle and then extend that triangle out in all 3 directions. And what you end up with there is a plane. So an equation with 3 variables, the graph of an equation with 3 variables is a plane. It's kind of like a sheet of paper. A sheet of paper is a perfect example of a plane. You can make a triangle and then extend that triangle out in all directions, and you end up with that sheet of paper or that plane. So once again, to graph an equation in 3 variables, find the intercepts by substituting zeros in. And once you get those intercepts, make a triangle out of those 3 intercepts, and then extend that triangle out in 3 directions. That is the graph of that equation, x plus y plus z equals 3. You can show the solutions of a 3-variable system. In other words, a system of 3 equations with 3 variables. You can show that graphically as the intersection of planes. So if you have 3 equations with 3 variables, one equation with 3 variables is a plane. So 3 equations with 3 variables would consist of 3 planes. So here are examples of 3 planes, intersecting or not intersecting. A system of 3 equations may have one solution. That would be one point of intersection. So if you have 3 planes, they may intersect at one point. There would be one solution. In other words, one point with x, y, and z coordinates. You may have no solution, no point of intersection. So you could have 3 planes. Imagine 3 sheets of paper with no points of intersection. In other words, they would be parallel planes. Or you could have infinite solutions, where they intersect in a line. So if you have 3 planes, or imagine 3 sheets of paper all intersecting in a line, they would contain an infinite number of intersecting points. So with these examples here, we're going to go around and tell whether these examples have one solution, no solution, or infinite solutions. So that first one, you see, imagine 3 sheets of paper not intersecting at all, 3 sheets of paper that do not intersect with 3 planes that do not intersect. There would be no solution. They have no point or points of intersection. The second example there, you see these 3 planes and they are intersecting in a line. They all come together and meet in a straight line. So those three planes meeting in a straight line, if they meet in a straight line, there would be an infinite number of points on that straight line. So for that, there would be an infinite number of solutions. We're here to the right. You have these three planes hooking together, but they all hook together at one point. So they all have one point of intersection or one solution. Down here at the bottom, these three planes, do they all come together at one point, or do they all come together at one line? No, they do not. There is no solution. Now, those are not parallel planes, but there is no solution. They do not all three hook together at one point or at one line. Then another example here. Ask yourself, do these three planes come together at one point or one line? Because if they come together at one point, that's one solution. If they come together at one line, that's infinite solutions. But these do not all hook together in the same place. So that, again, is no solution. So just because it's no solution doesn't mean they're parallel. You could have three planes that do not hook together in one point or one line, and there's still no solution there. There's no common point of intersection for all three of those planes together. Infinite solutions, they all meet in one line. And one solution, all three planes meet at one point. So those are the examples of one solution, no solution, infinite solutions for three planes, or three equations with three variables. We're going to solve a system of three equations in three variables. For example, these three equations, three different variables, x, y, and z. We're going to solve that system for x, y, and z. These are the steps. First step is to choose any two equations and eliminate one variable. So choose any pair of equations. It doesn't matter which pair. Eliminate one of the variables, either x, y, or z. Then the second step would be to choose a different pair of equations and eliminate the same variable as what you eliminated the first time. So choose a totally different pair than what you chose the first time. Now one of the equations will be the same, but as a pair they will be different. Eliminate the same variable as what you eliminated in that first step. So then you'll have two new equations in two variables. For example, in your first round, if you eliminated the z, second round you eliminate the z again, then you'll have two equations in two variables, x and y, and we've solved those before. You'll solve that system of two equations in two variables. And then the fourth step is to keep substituting in until all the variables are solved for. So as soon as you get the value of one of the variables, either x, y, or z, that's a key that's going to unlock the door to all the other variables. So once you know the value of one variable, you can find the value of all the other variables. Those are the steps to solve a system of three equations in three variables. Going to solve this system of three equations and three variables. Going to see if they have a point of intersection. And that point of intersection would have coordinates of x, y, and z. So the first step is to choose one pair of equations and eliminate one variable. It does not matter which two equations you choose. You can choose any two equations. For example, if you wanted to eliminate the x, you could go with the first and third. That would be an easy way to eliminate the x. If you want to eliminate the y, you could go with the second and third. You could easily eliminate the y there, multiply the third equation by 2. And if you wanted to eliminate the z, you could easily choose the first and third equation, multiply that first equation by 4, and eliminate the z. So there are many, many ways you could start this. But again, choose two equations, eliminate one variable. For this, I'm going to choose the second and the third equations. And I'm going to eliminate the y. So to eliminate the y, I'm going to multiply that bottom equation now by 2. So if you take that bottom equation there by 2, first equation there will stay the same. It's going to stay 3x plus 2y minus 2z equals 3. The bottom equation now becomes 4x minus 2y minus 8z equals negative 14. So you can see now when I add these together, the y's will be eliminated. That's what I want to have happen. I want one of the variables to disappear. So when I add these together, it's 7x minus 10z equals negative 11. I'm going to hold on to that because I'm going to use that in a little bit. So just keep that equation, circle it, mark it somehow so you remember where it's at, and then go back and choose a different pair of equations, which is the second step. So choose a different pair of equations than what you chose the first time and eliminate the same variable. So I have to choose a different pair of equations and eliminate the y again. So for this second round, I'm going to go with the first and third equations. So first and third equations, and I'm going to eliminate, as I did the first round, the y again. So to eliminate the y there, I'm going to multiply that bottom equation here by 3. That top equation is going to stay the same. So The top equation stays the same. Multiply the bottom by 3, you get 6x minus 3y minus 12z equals negative 21. So now when I add these together, the y will be eliminated, just as it was up here. So if you add those two equations together, negative x plus 6x is 5x, z and negative 12z is negative 11z, and negative 10 and negative 21 would be negative 31. So you can see now I have two equations in two variables, and we've done this before. So I'm going to solve those two equations for one of the variables, most likely by the elimination method. So I'm going to take those two new equations that I just got. I'm going to eliminate one of those variables and solve for the other variable. So 7x minus 10z equals negative 11, and 5x minus 11z equals negative 31. You could eliminate the x or the z. It does not matter which variable you eliminate and which variable you solve for. So for this, I'm going to multiply the top by negative 5 and bottom equation by 7 so that the x gets eliminated. Remember, as soon as I solve for one of the variables, as soon as I find the value of one of the variables, that's a key that's going to unlock the door to all the other variables. So take the top by negative 5, get negative 35x plus 50z equals 55. And the bottom equation by 7, it's 35x minus 77z equals negative 217. If you add those together, the x's will be eliminated. That's what you want to have happen, because then you can solve for z. Add those together, get negative 27z equals negative 162. Then divide each side by negative 27 and z equals 6. So that's the key that's going to unlock the door to all the other variables. As soon as I know the value of one of the variables, I can start substituting in. So right there I know z is 6. I can go back here to one of these two equations, substitute 6 in for z, and find the value of x. And it does not matter which equation you use. Anything up here is open game to use at any time. So I'm going to take one of those two equations that are circled. I'm going to take that top equation, 7x minus 10z equals negative 11. I know the value of z is 6, so substitute that in. Put 6 in for z. Or I'm sorry, 6 in for z. Yeah, 6 in for z, so it's 7x minus 10 times 6 equals negative 11. Get 7x minus 60 equals negative 11. Add 60 to both sides. Have 7x equals 49. Then divide each side by 7, x equals 7. So now I know the value of two of the variables. Two of the three variables I know. I know that x is 7 and z is 6. Still need to find y though. So you go back up here where there's an x, a y, and a z. Because I know the value of x, I know the value of z, I just have to find the value of y. So if you go back to the beginning, choose one of those equations and substitute 7 in for x and 6 in for z. It does not matter which equation you choose. So I'm going to go with that first equation, negative x plus 3y plus z equals negative 10. I know that z is 6 and x is 7, so substitute those in. Put 7 in for x, 6 in for z, and then I can solve this equation for y. Combine the like terms, negative 7 and 6, it's negative 1, so 3y minus 1 equals negative 10. Add 1 to both sides, you have 3y equals negative 9, and then y is negative 3. So the value of x is 7, the value of y is negative 3, and the value of z is 6. So we have three planes here, and these three planes all meet at the point with coordinates 7, negative 3, and positive 6. I'm going to solve these three equations in three variables. I'm going to solve for x, y, and z. The first step is to choose two equations and eliminate one of the variables. It does not matter which two equations you choose. Anything up there is open game. So just choose two equations, eliminate one of the variables, and you can eliminate it however you want. You could subtract, you could multiply by something, and then add the equations together. However you do it, just eliminate one of the variables. So I'm going to take that first equation and the second equation, first and second, and you can eliminate the x, y, or z. It does not matter. I'm going to multiply that top equation by negative 1, so I'm going to be eliminating the x. If you take the top by negative 1, you get negative x minus y minus z equals negative 1. The bottom equation then stays the same. So now when I add these two equations together, the x's will be eliminated. That's what I want to have happen. I want to eliminate one of the variables. Add negative y and 3y is 2y, negative z and 7z is 6z, and negative 1 and 13 is 12. Now that equation I'm going to hold on to. I'm going to use that in a little bit. So circle it, mark it somehow so you remember where it's at, because you're going to be using that shortly. Then go back and choose a different pair of equations from the original three and eliminate the same variable. So we'll have to eliminate the x again. For this, I'm going to go with the second equation up there and the third equation. So second and third equations, I need to eliminate the x again. So to eliminate the x, you can do it however you want. Again, I'm going to multiply that first equation by -1. So if we take that first equation there by -1, just change all the signs, get -x minus 3y minus 7z equals -13. Bottom equation there stays the same. It stays as x plus 2y plus 3z equals 4. Now, if I add these together, the x's will be eliminated. That's what I want to have happen. I want to eliminate the same variables what I eliminated in the first round. So eliminate the x by adding those together, get -3y plus 2y, that is -y. -7z plus 3z is -4z, and -13 plus 4 is -9. So there I have another equation in variables of y and z, just like this equation up here. So I'm going to take those two equations together and put those together to solve for one of the variables. So those two new equations that I just got, I'm going to eliminate one of those variables and solve for the other variable. The y looks pretty easy to eliminate. I'll only have to multiply by the bottom equation by something. So multiply the bottom equation by 2. Top equation will stay the same. If you take that bottom equation by 2, you end up with -2y minus 8z is equal to -18. So now if I add these two together, the y's will be eliminated, and then I can solve for z. So add those together, 6z and -8z, that is -2z. 12 and -18 is -6. So with -2z equals -6, divide each side by -2. Value of z is 3. As soon as I get the value of one of the variables, that's a key that's going to unlock the door to all of the other variables. So now that I know z is 3, I can take that and substitute it into one of these two equations with variables of y and z in it. So it does not matter which equation you choose. Little advice, I'd stay away from negative numbers, stay away from big numbers. Those seem to cause mistakes. So I'm going to take that first circled equation. I know that z is 3. Substitute 3 in for z, so it'd be 2y plus 6 times 3 equals 12. Multiply 6 by 3 is 18. Subtract 18 from each side. End up with 2y equals -6, and then the value of y is -3. So I'm almost there. I know the value of z is 3. I now know the value of y is -3. Now I need to find the value of x. So if I know y is -3 and z is 3, go back up here, anywhere up here where there's an x, a y, and a z in it, and find x. Because you know the value of y, you know the value of z, you can easily find the value of x. So I go back to one of these three original equations. It does not matter which equation you choose. Pick one that's easy to work with. That first equation looks the easiest to work with. Substitute 3 in for z and -3 in for y. So the x plus a -3 plus 3 equals 1. Well, plus a -3, that's -3. -3 plus 3 is 0, so those two cancel each other out. End up with x equals 1. So there are all three variables. X equals 1, y equals -3, and z equals 3. So these three equations and three variables, those are three planes. And those three planes meet at one point. That point has three coordinates. 1, -3, and 3. That is the point of intersection of those three planes.